So the thing I said to you yesterday about this was that a linear approximation is really just the slope of the tangent line. That's all it is. And as long as you're near the point of tangency, where they're touching, the answer, if you plug a number into the equation or you plug a number into the tangent line, you're going to get answers that are very close to each other. That's the premise of this. The whole goal of this, the why part of this, is that sometimes in the calculus, evaluating a function is very difficult for whatever reason. But evaluating a point on a line is a much easier process. So if you're somehow able to find out what the equation of the tangent line is, that's going to be a reasonable approximation of the function value at that point. Kind of like what we did last year when we did the what's the word I'm looking for here? The regression lines. We found some line that was a good approximation of all the points, and we just plugged a number into the line, and that would give us an estimate of what was going on. So same kind of an idea. So graph these two real fast on your calculator. Take a look at what they look like. Sine of x, of course, we're going to always be in radians, and then the line y equals x. And kind of zoom in a little bit, see what's going on with that. We'll pause here for a second. So what you should see is something kind of sort of like that if you zoom in a little bit. Kind of cuts up the middle. And yep. All right, so far so good. So it looks like that. So here's the point. That as long as I'm near the point of tangency, and by the way, the tangent line at 0 for the sine of x is y equals x. But we'll look at that. Zoom in a little bit around that point, and what you get is exactly what we kind of have been dealing with tangent lines. Now, this is one of those really weird, kind of unique situations where the tangent line actually cuts through at this point. It is a tangent line at that point. It's just that the curve changes direction. So the phrase I'm going to use a lot this year is the idea of locally linear. Even though obviously the sine curve is a curve, it zigs and zags, it does all sorts of things. If you zoom in enough, a graph is locally linear. And so that should look like it's zoomed in a bunch.
Yeah, I messed up. I clicked on it.
Okay. All right, so for small values of x, and by small values I mean points near 0 in this case, because that's where they're tangent to each other. So for small values of x, or in other words, for points near the point of tangency, the sine of x is approximately equal to x. You take any value, small number for x, and take the sine of it, it's going to be very close to the original number. The sine of 0 is 0. The sine of 0.0001 is going to be a number really, really close to 0.0001. Roman numeral 2, kind of a different idea. They're obviously related, but that was just kind of a, okay, tuck that in the back of your head kind of an idea. So look at this equation. This looks like something really nasty, doesn't it? It's not so bad, actually. This is something you should recognize. If I were to take this f of a back over to the other side, I would get this. That is something you definitely should recognize, because what that is just the point slope formula. Y minus the y value equals the slope times x minus the x value. F prime of a, of course, is the slope at that particular point. That is, if you plug in a, what you're finding is the tangent line at the point of where they intersect. at A. You're finding the tangent line at A when you do that. Now what the book does is calls that the linearization of f at A. It sounds really impressive, doesn't it? But all you're doing is finding the equation of the tangent line. They changed the y in the problem to a L of x. But don't get psyched out by that. It's just the equation of the tangent line. As long as you're near A, the function and the tangent line are very good approximations of each other. So now we already know the answer to this problem. The linearization of sine of x at 0 is x. We already did that by kind of intuitively just kind of looking at the graph of it. But let's use this equation to actually solve through the problem and show it. So the linearization of the sine of x at A equals 0. So f of A, f of 0, f prime of A, derivative of the sine is the cosine, x minus 0. So sine of 0 is 0. Cosine of 0 is 1. X minus 0, and sure enough, solve the equation, you just get x. Woohoo! That's the linearization of the sine of x at A equals 0. It's the equation of the tangent line. Already said this, right? Sine of x equals x for values of x near 0. And it really should be an approximating. You ever see that notation where you put the equal sign with a dot over it? Usually when we do equal signs that are approximations, we do little squiggly equal signs. I think they did this symbol. I think they came up with this because they would start to write the equal sign and they go, oh, no, wait, it's supposed to be an approximation. And so then they have to go back. So instead of erasing, they just put the dot over it. So sometimes you'll see that. That means approximately equal to. Nothing magical about it. And I totally made that up, but that makes sense to me. All right, so watch this now. Most of these problems that we're doing are actually kind of dumb problems because if I wanted to find out what the square root of 3.98 was, I would just take my calculator out and take the square root of 3.98. But we're going to use this to kind of show how this can be applied in more complicated kinds of things. So here's this graph. I was having fun with colors one day. Here's this equation, square root of x plus 3. And by the way, we should have a pretty good idea of what that looks like. The plus 3 inside with the x, you remember what that does to the equation?
It shifts it.
In with the x. So, well, in with the x, it affects the graph in the x direction. The same or opposite when it's in with the x. It's the opposite. So what's going to happen is this graph's going to go left 3 units. So it's going to do this. So what I want to do is estimate these two values. Well, here's what you want to see, is that both of these numbers are really near the number 4. And so this is just a little bit away. This is just a little bit away. Oh, actually, I take that back. Those are both numbers near 3, sort of near 3. They're closer to 4. Here's what I'm going to do. Hold on. Let me get ahead of myself here, and then I'll come back for a second. Well, shoot. Okay, never mind. I save that thought for a second. Find the linearization. Let me just do that. I was getting ahead of myself. So in order to find the linearization, I need to know, let me back up. I need to know the function. I need to know the derivative. So I'm going to find the function and the derivative. So there's the function, the derivative of this guy. Remember, this is x plus 3 to the 1/2 power. And so the 1/2 comes down, exponent gets smaller by 1. And then the negative puts it back in the denominator. So now let's plug it into that equation. So I need f of a. What I wanted to do, and this is, did it say at 1? I didn't read the problem. Yes, it did. I'm sorry. I didn't read the problem right. So at 1. Okay. That's the piece I was missing. So f of 1, f prime of 1, there's the derivative, plug stuff in. When I plug 1 into that equation, remember it was square root of x plus 3, so that becomes square root of 4. That's where I get 2. The derivative, plug 1 into here. I'm going to have 1 over 2 times square root of 4. That's 2 times 2 is 4. It's 1/4. So that's where those two values come from. All right. So now let's plug it back into the equation. And I come up with, after I simplify a little bit, bingo. Which, of course, is just a line, right? 1/4 x plus 7/4. All right. So what that's saying is I found the linearization of the square root of x plus 3 at a equals 1. X equals 1. So those two equations, if you were to graph them and zoom in, they would look exactly the same. Now, let's do this estimation. 1 was my x value, which means, remember, it was x plus 3. So near 1, if I put in 1, this is 4, that's a number near 4. That's what I was wanting to get at before. So if x is 1, this is then, what this would become is 3 plus 0.98. I'm near 1. If x is 1, this would be 3 plus 1.05. That's near 1. So as long as I'm near 1, this equation, this red stuff, is going to give me an answer that will be a very good approximation of what the square root would be equal to.
So back home, no, 4-2. There. So it's so when you're estimating that, that's not estimate x equals that. That's x plus 3 equals 3.98. Is that what? Like,
yes. X plus 3 is equal to 3.98, which means x is equal to 0.98. So I found the linearization at 1. And 0.98 is a number near 1. So when I want to find this answer, I can try to figure out what the square root of 3.98 is, or I can use the linearization to estimate what the value of the square root of 3.98 is. Those are those two values then. So that's what I was showing a second ago. So what I can do then is plug in what the x value is into this equation. Remember, it was 7/4 plus 1/4, or I can just do it as x over 4. Plug the 0.98 into there, and I get this. That's the actual real answer when I plugged it into the calculator and checked it. And by golly, it's a pretty good estimation of the value. Again, these are kind of silly problems in this level because I could just plug this into the calculator and get an answer. That's kind of not the point. We're trying to get the idea of the linearization and the being able to use the tangent line to estimate the function value. We're just picking easy problems for now. And then I did the same thing with, we still going here? Yeah. With the other one. Now, since x was the 1.05, plug the 1.05 in, do this arithmetic, come up with this answer, the actual answer being this guy. Those are pretty daggone close to each other. I mean, down to tens, hundreds, thousands, within a 10,000th of the right answer. So, remember I said that answer was accurate to within the 10,000ths of a unit. What if I wanted to set the limits? And this is the kind of thing that in industry that you will sometimes have. What are the boundaries that I can establish that will give me an answer that will be accurate to within a certain value? This is going to be a calculator thing that we're going to play with. This is kind of an interesting problem. I want these two things to be within 0.5 of each other. Now think about what a curve and a tangent line looks like. And I talked about this a little while yesterday with you. missed it. Let me try that one again. That's a little better. Okay. Does it make sense that as long as you're close, the blue line, the curve, the red, the curve, are going to be close. But if you get too far away, they're not very close. The blue line is no longer a good estimate of the curve. How far over are you allowed to go before you reach something that's unacceptable? The 0.5 is an arbitrary number. Pick whatever number you want. But it may make sense to have this big. It may make sense to have that small. Whatever that value is, that's going to be the limits that make sense for the problem. I need for these two things to be within 0.5 of each other. Calculator, graph those two things and take a look at what the picture looks like. So now that you got those two things graphed, what I want you to do is to go into y sub 3 and graph the absolute value of y1 minus y2. And graph y sub 4, making it 0.5. But turn these two off. Remember how to do that? We go over to the equal sign and hit enter, and that'll turn them off. What you've got, the blue curve is the absolute value. That's the difference between the two. And you can see at 1, look at the difference between the two. 0. The red, purple, whatever color this is, the purple line represents 0.5. So I need for the difference between the two to be less than 0.5. Well, it happens starting here. To the left of this point, the difference is above 0.5. Too far apart. And when I come out to the other end, out there. And all I did to find these was do an intersection on the calculator, find where those two graphs cross each other. So now I know, as long as I pick a number between negative 2.657 and 8.656, the linearization will be accurate to within 0.5. I might need to be more accurate, in which case I could change this equation. Instead of this equation being y equals 0.5, maybe I make it y equals 0.05. Now, obviously, that's going to drop the line down shorter. And if I drop that line lower, now you're going to get new intersection points, right? This one's going to be in much closer, and this one intersects much closer over here on the right. Same idea, though. Find those points of intersection, and now I'm accurate within 2.05, et cetera, et cetera. Last idea. This was the part you said you read you weren't quite sure about. The phrase differential is simply talking about this notation, dy dx. The differential, the difference in the x values, the difference in the y values. We know this from a long time ago, right? dy dx means f prime of x. Mostly we've been thinking of that as just kind of one thing, the derivative of y with respect to x. But in some situations, you can think of it as an actual ratio. Difference in the y values over difference in the x values. And because I can think of it as a true fraction, an actual ratio, I can multiply both sides by dx. And so, look what this is saying. The difference in the y values is going to be related to the slope and the difference in the x values. In other words, how far over you go multiplied by the rate at which you're going up is going to tell you something about how high up you go. Right? This is telling you how far over you go, what was the change in the x, how steep is the line, and that's going to tell you how high up you went. If I go over 1 unit and my slope is a half, I don't go up very far. If I go over 1 unit and my slope is 1,000, I'm going to go up very high, right? So the combination of how far over and how steeply you're doing that as you go over is going to tell you how high up you go. just kind of be able to read the vocabulary and not get freaked out. The differential dy, differential, the difference in the y. So the differential dy is defined in terms of x and dx. This is f of x is a function, f prime of x rather, is a function of x. So it's about the change in x and the place where you are, or I'm sorry, the steepness of the slope. So here's how this is going to work out. The change in x is just this guy down here, right? On this linearization equation, I'm going to combine a couple ideas here. This is just the change in x. So I'm going to replace that with dx instead. Oh, but by the way, back over here, remember what it says? F prime of x, this says f prime of x dx is dy. So f prime of x dx is dy. So when I get to this step, I can take f prime of x dx and replace it with dy. Now think about what this equation is saying right here. The linearization has to do with the function value plus the change in the y. So when you move over a little bit, how far up are you going? What's the change in the y value? Look how this plays out. I'm going to do the same kind of a thing that we did before. I'm going to do an estimation, but I'm going to do it in just ever so slightly a different way. Estimate 36.1. Well, the function is square root of x. And I'm really, really close to the point where a is 36. But I've changed the x values by 0.1. So the change in x is 0.1. So according to that equation we had a minute ago, the dy is simply f prime of x dx. So I got to find the derivative. Well, the derivative of x to the 1/2 is 1/2 x to the negative 1/2. That negative puts it in the denominator, so you get 1/2, and then x to the 1/2 in the denominator is square root of x. So that's where this line comes from. Now, dy or dx, there it is right there, right? Dx is 0.1. So the change in y on this problem, the change in y, well, at a equals 36, I plug in 2, square root of 36 is 6, times 0.1, which is the same as 1/10, right? This is equal to 1/10, so that's why I end up with a 10 down there. Multiply all that together, I get 1/20. 1/120. That's the change in the y value. That's the change in the y value. Now, go back to the rest of the equation. What I just found was this guy. Now I got to go back to the rest of the linearization. F of a 6, add 1/120 to that. So what I've done, without having to really do too much work in terms of real hard calculation, I can find the square root of 36.1, a pretty good estimation, without touching the calculator. Now, changing 1/121 to a decimal might be a little tricky, but this is equal to 6 plus 1/120, or 6 and 1/120ths. All right, one more last example. The differential of the function, the dy, is what you're looking for. That's what it would set up as. And so I need f prime, so take a derivative. And what was the point I was at when x is -2? So now, plug in the -2. Plug in the 0.1, the dx. And whack away at it. So what that's getting you is it's telling you what the change in y is based upon this change in x. The change in x in this case was 0.1. The change in y at that point on the graph is going to be 4.1. So when you slide over 0.1, the y is changing by 4.1. The end.